Who's ready for an adventure? My name is Giovanna from ESA Education, and welcome to Webb Quest, mind-blowing mission to the early universe. We're at the European Space Agency's Technical Center in the Netherlands, where we're setting off on our quest to the stars and back to the early universe. And we're not going alone. Our guides today are ESA astronomers Mark McCaughrean and Giovanna Giardino. And I have tons of questions for them, like what's so amazing about the Webb Space Telescope and what is actually its mission? What do we know about the early universe and how is Webb going to change that? And what does any of that have to do with you? Yes, you. Now, I've got a few things to help us along the way because you never go on a quest empty-handed, like a telescope, pretty relevant to today's discussion, an apple, because we are traveling billions of light years, so it's important to pack a healthy snack. And of course, Paxi, because who doesn't love Paxi? So grab what you might need for today's quest and let's get going. I'm off to find our experts, Mark and Giovanna. In the meantime, relive an important moment in human history, the launch of Webb, the world's most powerful space telescope so far. See you in a bit. Mark, Giovanna, hi.
Hi.
Thank you so much for being our guides today on Webb Quest. Now, I know that we're in good hands, but just to reassure everyone watching that they're in good hands as well, can you introduce yourselves and tell us a little bit about your background?
Yes, I'm Mark McCaughrean. I'm the Senior Advisor for Science and Exploration here at the European Space Agency, which means that I get to talk about all of the missions that we fly for astronomy and planetary science and also going to the Moon and Mars. But my first love as an astronomer is the James Webb Space Telescope. I'm a member of the Science Working Group for JWST and will be using the telescope to do science very soon.
Thank you. Look forward to hearing more about that. And Giovanna?
Yes, my name is Giovanna Giardino and I'm also an astronomer at ESA, supporting the near-infrared spectrograph, which is the one of the scientific instruments on board of this Webb Space Telescope.
Wonderful. Now, I have with me here a telescope, or what most people traditionally think of when they hear the word telescope. But this looks absolutely nothing like the James Webb Space Telescope, and yet it's still a telescope. So maybe we can start here and you can explain to us how Webb is a telescope.
Sure.
Mark, maybe grab a coffee and
you.
we'll connect with you in a sec.
See you in a few minutes.
So that's a very good point, right? What is a telescope? And a telescope, the main elements of telescope are really the mirror, or if it's a small telescope, you can also use lenses that we use to capture the light. And those are the elements that define the Webb Space Telescope, just like your little tube telescope, which probably contains lenses. So this is the primary mirror of the telescope, which is the big collector, like a big bucket of light that collects lots of light coming from the different objects that we see in the sky, stars, galaxies, planets. And it focuses on this secondary mirror that then focuses the light inside this hole that you see here. And behind here, we have the scientific instruments. A camera, a spectrograph, and these scientific instruments collects and records the light that comes through the primary mirror, whatever is pointing in the sky. So those are the main elements.
Now, and does every telescope have this cool little cape.
No. So what's special about the Webb Space Telescope? It's optimized for observation in the near and mid-infrared. And that's also the reason about this striking gold coating that you see here. The 18 hexagonal segments are coated in gold because that's the best metal to reflect in the infrared. Now, as you know, when maybe you've seen an infrared camera, every object that has a temperature, a certain temperature, emits in the infrared. So if you want to observe far away weak objects, you have to make sure you have a cold instrument that doesn't blind the weak signal coming from the sky with its own emission because it's warm. So that's the reason for this very large sun shield. When in space, the Webb is oriented in such a way that the Earth and the Sun are always behind the sun shield, and the primary mirror is pointing in deep space. You know, deep space is very cold. It's a temperature we say of 3 Kelvin, so minus 270 degrees Celsius, extremely cold. So by keeping the telescope always in the shade, we can cool it down to really low temperature, about minus 230 degrees. In this way, we have a cold telescope and we can make very sensitive observation in the near infrared. So that's really the reason of this sunshade. It's really crucial. That's why everybody was very tense when he had to unfold his face, but everything went fine.
So what about the famed honeycomb structure? Why is it such a cool shape?
Yes, sure. So as you know, the primary mirror is large, it's 6.5 meters in diameters. So we had to design a segmented mirror that could be folded. And that's why it's not a unique surface, but it's got these segments and the two wings, these two lateral wings fold at the back. You can see here actually, this is how the Webb telescope was launched and stored into the fairing of the Ariane 5, the rockets that launched it. You can see that the two lateral wings of the primary mirror are folded on the back, and then the huge sun shield is folded onto itself and around the telescope in such a compact configuration that it nicely fits into this fairing of the Ariane 5 rockets. That was a huge challenge in the design of the Webb, having to combine large size but at the same time foldable to be able to launch it. This is one of the biggest fairing that you can have in terms of rocket size.
So on the subject of the sun shield, we got a very interesting question from Anthony's students in the UK. And they were wondering whether it's possible to build a giant sun shield around the Earth to help cool it down.
Wow. It's an interesting question. I think the idea, it's there. Obviously, if you have a shade, if you can somehow shade away part of the sun, you will have a cooling effect. But the technology, it's not immediately transportable, definitely, from this relatively small. It's big, it's the size of a tennis court, but it's nowhere near the size you would need to achieve cooling. And our infrastructure, I mean, from a practical point of view, I think it's still far away.
Yeah, it's not the most practical solution for climate change, is
no,
it?
it's not the most immediate blue.
And what about the detectors on James Webb Space Telescope? Because on the normal telescope, the traditional one, you use your eye to detect it, especially on Earth. What's doing that out in space?
So mounted here at the back of the telescope, we have 4 scientific instruments. 3 operate in what we call the near infrared, and 1 to optimize for observation in the mid infrared, so even colder objects if you wish. The near infrared instrument, we have a camera and a spectrograph. Cameras record the images just like your camera on your phone or portable camera, with the difference that this camera is very sensitive, extremely sensitive, and very advanced technology, obviously, as it operates behind this telescope. We have a spectrograph. The near infrared spectrograph is one of the main contributions of ESA to this mission. And with the spectrograph, we can analyze the components of light. We have a prism and also grating, so like the prism splits the light from a white light source into the rainbow component that you see coming out from a prism. We do exactly that with the near infrared. It's not visible from your eyes, but our camera records the spectra, the components. And in this spectra, we can see the signature of elements that are present in the astronomical object that we are looking for. So you can imagine that if we point the Webb telescope to what we call an exoplanet, so a planet orbiting a star rather than the sun, we can analyze, for instance, the atmospheres of this planet and understand what type of elements are present in this atmosphere. Is oxygen present, water vapor, methane? So that's the power of a spectrograph combined with the images that tells us the shapes of the object. The spectrograph tells us the physics and the composition.
So a lot of you have asked us how and why Webb observes the universe in the infrared. And in order to answer those questions, we need to understand a little bit more about light and electromagnetic radiation. Nora Lutskendorf is an ESA astronomer based at the Space Telescope Science Institute in the United States, and she breaks down the spectrum of light for us. Take a look.
Hi, my name is Nora Lutskendorf and I'm an astronomer at the European Space Agency. Today I want to talk about light and the electromagnetic spectrum. First of all, what is light? Light, or visible light, is just one part of electromagnetic radiation. This kind of radiation can be seen as a wave, similar to the wave that you see when you throw in a stone in a lake, or a very fast particle that moves with the speed of light. But for today, we're just going to be talking about the wave character. So visible light is everything you see around you. It comes from the light inside your house or the light from the sun. You sometimes even see it split up in its components, the different colors, when you look at a rainbow. Our eyes are only equipped to see visible light, but there is actually so much more to the electromagnetic spectrum than this. Let's take the wavelength of the visible light, for example. This wavelength is in the order of 100 nanometers. This is as big as the point of a needle or maybe a single-cell organism. If you make that wavelength even smaller, to the size of a molecule, you get what we call ultraviolet light. You cannot see that light, but it would probably look very violet. It is the light that actually produces vitamin D in our skin and makes our skin tan. It comes from the sun, but again, we cannot see it. Now making this wavelength even smaller, to the size of an atom, then we get what we call X-ray radiation. You have seen this before in your doctor's office, because X-ray radiation can actually go through our skin and reveal our bones. Making it even smaller than this, so 100 times smaller than an atom, to make it to the size of the core of an atom, you will get gamma ray radiation. Gamma ray radiation is very energetic radiation, which we don't see very often on Earth, but we have seen it in the universe. Very big events such as supermassive black holes merging can produce gamma ray radiation. Now let's go to the other side of the spectrum. Let's make the wavelength bigger. If we make it as big as a blood cell, or maybe even the thickness of a hair, we get what we call infrared radiation. Infrared radiation is also called heat radiation. You might have seen it when you look at the heat camera and you see which body parts are hot and which are cold. All bodies in the universe actually emit heat radiation. It doesn't matter if they're cold or hot. And we cannot see this radiation either, but sometimes we can feel it. Making it bigger, to the size of an insect, going from 3 millimeters to 30 centimeters, we are coming into the regime of the microwave radiation. You have something like this in your own kitchen. A microwave uses microwave radiation to heat up water. Making it bigger than this, going to the biggest wavelengths that we have in the electromagnetic spectrum, going to 100 meters and bigger, it's what we call radio radiation. Those are such long wavelengths that they are able to travel very, very far and undisturbed. And that's why we use this a lot for communication. Radio radiation can be transmitted and also received from those really big radio dishes that you often see. Now you have seen that light is only one small part of the electromagnetic spectrum. So if we observe the universe only in the visible light, we wouldn't see much. We would only see a very small part of the universe. Luckily, we have developed instruments and telescopes that can observe the universe in different wavelengths. Those different parts of the electromagnetic spectrum reveal different parts of the universe. Take infrared, for example. Because of the size of the wavelength of the visible light, which is about the same size as the dust particles in our universe, visible light cannot go through dust because it will be absorbed and scattered by those dust particles. However, if you have longer wavelengths, such as the infrared, they can go through dust unnoticed. This is the reason why telescopes that observe in the visible, such as the Hubble Space Telescope, gave us those amazing images. But whenever you observe a dust lane, you would see just a dark spot on the image. Telescopes that observe in the infrared, such as this James Webb Space Telescope, will be able to look what's behind this dust. This is really important for objects such as supermassive black holes in the centers of galaxies because they sit behind big dust lanes, but also for the birthplaces of stars and planets who sit in dust and gas clouds that they were formed of. Out in space, away from the hot and busy Earth, the James Webb Space Telescope will be able to observe a whole new world for astronomers in the infrared.
So Mark, Nora made this really interesting statement. She said that Webb is going to open up a whole new world for astronomers in the infrared. And besides that being a fascinating topic that I hope you can break down for us, it begs the question, what do we already know about the universe? And how is Webb going to potentially change that knowledge?
Well, the most important thing perhaps we know about the universe is that it hasn't existed forever. It was actually born about 13.8 billion years ago in this thing we call the Big Bang. At that point, the universe was tiny, much, much smaller than the space between my fingers. And it rapidly expanded to become this massive object we see around us today. And it's continuing to expand today. But what this means is that at some point the universe was, when it was very young, was full of very hot elementary particles which formed gas, and then that gas cooled down. There was a point at which there was essentially nothing in the universe except cold gas. There was nothing to see. But maybe 100 million years after the Big Bang, gravity began to pull that gas together. And as that gas spiraled down and collapsed, it heated up, and it started forming things we now call stars. So the first stars that ever formed after the Big Bang, these are objects which we can predict, and we can have some ideas about the properties of those objects, but we've never been able to see them. The James Webb Space Telescope is so big that it can detect the light from those incredibly faint objects because, of course, now they're very far back in time, they're very far from us, so they're very faint objects. And we also need to look in the infrared because the universe is expanding, continuing to expand, and that stretches the light out, and it moves the light from the visible wavelengths, the optical, which we can see where the light was originally emitted. It's all been moved into the infrared, longer wavelengths, more stretched out. And so the Hubble Space Telescope has been able to see back to maybe a few 100 million years after the Big Bang, but it's already seeing objects which have evolved and changed. These aren't the first ones. The James Webb Space Telescope is designed to see the very first objects that formed in our universe after the Big Bang.
So a lot of telescopes are essentially time machines, but the way that James Webb Space Telescope is a time machine, how is that possible? A lot of students have asked us, how is it a time machine? How is it going to take us back in time?
Well, light doesn't travel instantly. Light travels at 300,000 kilometers per second. So that means, for example, the light we see coming from the sun actually left the sun 8 minutes ago. And when we look at the nearest stars around us, the light is years old already because they're light years away from us. That's what a light year means, the distance that light can travel in 1 year. The nearest galaxies to us are more like 1 million or 1.5 million years in the past. It's taken that long for light to get to us. So the further we look away, the further we look back in time. So essentially everything we do in astronomy is like being in a time machine and saying, what did the universe look like 1 billion years ago? Well, if we look far enough away, the light has taken 1 billion years to get to us. We see it as it was in the past. And here's the thing, it's not the same as it is today. The universe has been changing over time. So as we look at different distances, we look at different times, we can build up a picture of how things have changed, how the first stars formed, how the first galaxies were made, and how they've changed since. So the universe we have, the little bubble we have around us today, looks quite different to the way it used to be billions of years ago. And that's where Webb is so powerful in being able to look all the way from the nearby universe, times of just minutes or years away from us, all the way back 13.8 billion years into the past.
Now, where else can Webb take us in space? Because surely the most powerful space telescope ever built so far can do a lot more, right?
Absolutely. So once you've built a very big telescope to collect the faint light from those very first galaxies and stars, and you're in the infrared, it opens up a huge range of possibilities for doing other science. So Webb will be looking right from our own solar system, looking at the nearby planets, looking at Mars, Jupiter, Saturn, and out then into the dusty belt of icy bodies that sit around our solar system. It's a place we call the Kuiper Belt, where there are objects left over from the birth of the solar system sitting out there in the cold, and Webb will be able to see them. And then we can look in places where new stars and new planets are being born in our Milky Way galaxy today. Places just 1 million years old where these stars are still surrounded by gas and dust. And in invisible wavelengths, it's kind of hard to see in there because all that dust gets in the way. But we can go through the dust in the infrared and see the baby stars and their new planets being born right now. And then when we look further away, we can see all of those galaxies which are between the very first ones that formed and the Milky Way we're sitting in. We can look at how galaxies have changed over time. So that's the beauty of Webb. Once you build this observatory to do that one first big project, look at for the first galaxies and the first stars that ever formed, it opens up a huge range of other possibilities. And in fact, one thing we didn't even think about when we first started designing the telescope was looking at planets going around other stars, what we call exoplanets. But because we built such a powerful machine with some fantastic scientific instruments on the back, it turns out that it's perfectly suited to measuring the atmospheres of planets going around other stars. And by looking at their fingerprint, the fingerprint of light in the spectrum we can take, we'll be able to understand the chemistry and the physics of those atmospheres, maybe even find planets like our own, potentially even with signs of life in.
Wow, if you can break that down a bit more, because we got a really interesting question from Desiree and Trinity all the way from Trinidad and Tobago, and they ask us, how will Webb know which types of atmospheres are suitable for life?
Well, that's a great question, and we're definitely going to see lots of planets where you really, really wouldn't want to live. So we know, for example, that Venus is a planet which is very like the Earth in terms of its size. It's made of rock, and it's just a little bit closer to the sun. And our models would say that should have liquid water on it because it's just a bit warmer than the Earth. Well, actually, it's a lot warmer than the Earth because it has a dense clouds of sulfuric acid and then an atmosphere made of carbon dioxide. And Venus it's a hell. It's so hot, you really wouldn't want to go there. So this is the thing, is we need to go and actually measure the atmospheres of planets going around other stars to try to understand how the properties might be different. Even if you move a planet just a little bit closer to its star, a little bit further away, it can change the properties enormously. So what we'll be looking for are the kinds of gases we see in Earth's atmosphere, which is mostly nitrogen and oxygen, plus a few other trace gases, very small amounts of gas. And some of those gases we think might only come from processes which are involved with life. So for example, methane. On Earth, methane is almost all made through biology. It's made through animals. And if we can see methane in the atmosphere of another planet going around another star, well, who knows? Maybe that's
There might be farting cows.
Well,
on
maybe something going on there, right, like that. But we have to be careful. We have to find other things as well, because we know that methane in other planets might arise just from geology, for example. And so it's careful detective work. We won't be able to just take a spectrum and say, look, there it is. We can now see the signs of life. It's never going to be like that. It's going to be, well, maybe it's this and maybe it's that. Let's look at some more and see if we see the same features in different planets. So it's going to be very careful work. It's going to take a lot of time as well with a telescope, because these planets are very, very small and faint next to their very bright stars. So there won't be a eureka moment, we don't think, but it's worth spending a lot of time with this observatory if that's the kind of question we can answer.
And I'm curious as to when will we know if Webb's going to look at an exoplanet first, or if it's going to be looking at a galaxy or early stars? How is that factored into its schedule?
Yeah, well, the scheduling of the telescope is quite complicated, because the way that Webb is in space, going in orbit around L2, it has the sun and the Earth on one side all the time, so the telescope can get cold on the other side. And the telescope actually can spin around and look at an area on the sky, and what we call an annulus. And as the telescope goes around the sun with the Earth during a year, then the annulus changes. We can look at different parts of the sky at different times of the year, which also means we can't look everywhere at all times of the year. So the schedule, the way the schedule is built up, takes in all of the observations the astronomers want to do, different places in the sky, and says, well, we can only do that in March, we can do that in September, we can do this in June. We have a 2-week window for this observation. So that's very complicated work, and you don't really get to choose when you want your observations. Where your object is in the sky, that will make that choice for you.
Okay, thank you very much, Mark. Well, it's February 2022, so I think it's time for us to get a status update on Webb. So, Mark, Giovanna, I think everyone would like a status update on Webb. Can you tell us where it is right now, what it's doing, what we can expect in the coming weeks and months? Mark, let's start with you.
Yes, so on Christmas Day at the end of last year, we launched on this Ariane 5 rocket, and the main thing to do in the first couple of weeks was get it all unfolded from the state you see here into what you see over there. And that meant unfolding the mirrors, unfurling this giant tennis court-sized sun shield, and then we're now in the phase where we're trying to align the mirrors, because we have 18 of these hexagonal segments which make up the full main mirror. And at the moment, they're all pointing in slightly different directions. So if we take a picture today, and we'll take a picture, for one star, we'd actually see 18 images. So it's important that we tweak all the mirrors, all the positions, line them up so we have just one star. And then we have to wait for the instruments to cool down, turn the instruments on, get the electronics going, get the detectors going, get the little wheels and the other pieces of equipment inside the instruments which let us do the science. That's all quite a long, complicated process, because we have to take data, send it down to Earth, check it out, look at what that means. What do we have to turn now? Do we turn this knob? Do we flick this lever? How do we get all the instruments ready for doing science, at the same time as aligning the mirrors to make sure we just have one star at a time?
And how long is that going to take?
That's going to take us about 3 or 4 more months. So we launched at Christmas, and we'll be ready for science by the summer, around June this year, 2022.
And Giovanna, Webb has arrived at its location in space at Lagrange point 2. And actually, Christina from Spain would like to know a bit more about where Webb will be orbiting. So why Lagrange point 2? What's so special about this point in space? And is it fair to call it a sort of cosmic parking spot?
Yeah, it's an interesting take on it. Lagrange point 2 is a special point at a distance of 1.4 million kilometers from the Earth. That's about 4 times the Earth-Moon distance, so it's far away. It's not an orbit around the Earth like Hubble, for instance. It's in this area, parking lot, in the sense that it's orbiting around this point. So it's not a static parking lot, but it's kind of a dynamic parking lot in which the telescope orbits around this point, and this point orbits around the sun at the same speed as, synchronous with the Earth. why special? Why sending there? Well, there are a couple of reasons, but this point is normally chosen because it's where the gravitational pull of the Earth and the Sun are equalized by the centrifugal force. So it's an equilibrium point, and you need little fuel, relatively little fuel consumption, to keep the spacecraft in the orbit, in the attitude, and then to point the telescope. At the same time, it's ideal because you can keep the mirror, the primary mirror in the instrument, always pointed into deep space and in the shade of this huge sun shield. So observing into the space, always in the shade, the telescope is cooling down. That's what we need in order to observe it in the near infrared.
Okay. And Mark, we heard that the Webb Space Telescope's mission was initially for 10 years, but launch was so successful that we may have added some more time to that. Can you tell us a bit more?
Yeah, so the Ariane 5 was the thing that put us on the way towards this orbit around L2. And there was some margin in that, so we didn't know exactly how close it would get us on the right trajectory. And it turns out on the day that that rocket was perfectly tuned and put us on exactly the right trajectory, where just a couple more tweaks in the last few weeks have put us exactly into this orbit. And what that's meant is we've saved fuel on board. We use this fuel to adjust our orbit, and that we need to do during the mission over the coming years. So the more we can save at the beginning, the more we have left over for adjusting the orbit later and staying where we need to be around L2 to do science. So what we think happened is that we had such a precise trajectory from the Ariane 5 that we saved enough fuel to double the length of the mission. So going from 10 years to 20. Now, other things may fail inside that time. The mission was only designed for 10 years, so there are other bits of hardware that might not last that long. So we can't be sure yet that we'll last for a full 2 decades. It's very early days. We've only been in orbit for 6 weeks or so. But at least that part is probably out of the equation now. We don't have to worry so much as we did before the launch.
Okay. Now, Webb took decades to plan and to build and eventually to launch. At what point in its development did you enter the picture, and will you get a chance to sort of play with it, to do science with it? Let's start with Giovanna.
Yes, I joined the ESA team that is in charge of the development and calibration of the near-infrared spectrograph, NIRSPEC, that is on board. It's one of the advanced scientific instruments on board of the Webb Space Telescope more than 10 years ago, 11 years ago. So quite a while. It's been a fantastic adventure to see this instrument coming together and then being mounted on the telescope. My work definitely does not finish here. Now we are busy with what Mark was saying, calibrating the instrument, tuning it, and making it ready for the scientific observation from the community of astronomers. So it's a very exciting moment for me and our team.
Wonderful. And how about you, Mark?
Well, I've been involved even longer. I'm a bit older than Giovanna, so I've been on the project for almost 24 years. And I started by being invited to be part of what was called the Science Study Team for the European Space Agency back in 1998. And that was to look at how ESA might join in with NASA and the Canadian Space Agency in building a successor to the Hubble Space Telescope. At that point, we called it the Next Generation Space Telescope, and it's the thing we now know today as Webb. So I was on various committees that helped define the kind of science we wanted to do, the sorts of things we wanted to look at in the deep, distant universe, in our own Milky Way. And actually, it was before exoplanets, planets going around other stars, even before they were discovered mostly. And so that really wasn't part of the case initially for this machine. So we say, this is the science we want to do. What kind of telescope do we need to have to enable that? So there was design that went on for several years and then started to be built. And I've been a member of the Science Working Group, as it's called, the main science team for JWST for just about 20 years. And through that process, we've been making sure that every time the engineers said, well, let's cut this piece off, that's costing too much money, or let's change this thing. The scientists would say, oh, well, hold on, you can't get rid of that. If you do that, we won't be able to do the science we said we wanted to do. And there's a real working process between scientists and engineers. And so now where we are today is at that stage which the scientists are most excited about, finally being able to get data back take images, split the light up into a spectrum and analyze the chemistry and the physics of things in the universe. And so I'm really looking forward to that stage, because I wrote 20 years ago, this is what I want to do when we have the next generation space telescope, or the James Webb Space Telescope. And finally, now we're just months away from being able to make those observations.
Wow. Now, if we're talking a mission of 10 to 20 years, for instance, how that means students watching today can get involved and could use data from Webb. How does that process work? If you wanted to go and study astronomy and use Webb?
Yes, absolutely. I think the students that are watching today, some of them can join a team that will receive data from the Webb Space Telescope and maybe do their thesis, their project, their undergraduate project, their thesis, their PhD thesis, and have access to the data that the Webb will deliver. I think everybody working on a space mission always have in mind that some of the instruments will be used by the next generation. On top of that, the Webb Space Telescope is a general observer telescope, which means that any astronomer that has a certain level of understanding of how the telescope works can apply time, can ask for time for their own investigation to answer the pressing question that they have about astrophysics or astronomical process.
Mark, is it safe to say that it took a village to build James Webb?
It's actually more like a small town or a large town. About 10,000 people were involved along the way in the science community, academics who said, well, this is the kind of science we want to do, people in the space agencies, people in industry that put it all together. And that industry is in North America, in the United States and Canada, and spread all over Europe. So around 10,000 people over roughly 20 years. That's a huge amount of effort. And actually that's a really important lesson about how we get together as communities of different kinds of people, different talents, different expertise, different nationalities, different cultures, and solve big challenges. And that's something we've learned with Webb, but of course it's applicable to so many other things in life. You know, as we face climate change today, that's only going to be solved by people all around the world coming together and saying, this is important, let's make it happen. Let's deal with this problem that we have and solve it. So I think Webb is a brilliant example not only of astronomy and the science we can do it looking out into the universe, but it helps us look back here on the Earth as well about how we can build teams to solve big problems.
Wow. And you two, as people who worked on it from the beginning, you'll get to work with the data, but you've also helped build something that future students and astronomers will get to use. And I think that's wonderful. Congratulations to you both. And speaking of potential future astronomers, thank you to all the students who've sent us in questions. We received so many from here in Europe, but also worldwide from places like India and Brazil and Trinidad and Tobago even. And we hope the course of our conversations have answered most of those questions, but there are still a few more that we can pose to our experts now. So Giovanna, Webb is known as the successor to the Hubble Space Telescope. Right. But Bruno from Italy would like to know if there's already a successor to the Webb telescope planned.
It's not planned, but there are designs and ideas for possible successors, telescopes that are bigger and even more powerful. There is a talk about a telescope of similar design, so again modular design like the Webb, but with mirrors of up to 15 meters diameter against the 6.5 that we have here, so more than double. They will be an incredible challenge, but I think that's what's also important for the Webb of this project, of this large international collaboration like Mark was saying, is that also teaches us and we learn what's possible, what challenges we can overcome together. So yes, people are always coming up with new ideas.
Now, this question maybe you can help us with, Mark. There's all this talk of Webb, but Webb doesn't actually stand for the World Wide Web Telescope. Who was James Webb is a question from Guilherme in Portugal.
Normally we name our missions for scientists. So we have, for example, missions named that went to Saturn, Cassini, or Galileo, which went to Jupiter. And we have telescopes that look out into space like Hubble, named for Edwin Hubble. We also sometimes use more poetic names. Rosetta, the mission that went to the comet a few years ago. In this case, this mission has been named for James Webb, who was the administrator of NASA in the 1960s at the time of the Apollo moon landings. And he was also very involved in setting up a big space science program. So at the same time as sending humans into space, NASA was expanding into doing planetary sciences and astronomy and understanding the universe with, if you like, with robots. And the decision was made about 20 years ago by our NASA colleagues to name this observatory in his honor for that work that he'd done in the 1960s. So, but as you say, the coincidence there with the word web, as in World Wide Web, is, well, it's amusing at least, although there's no connection at all.
It's a happy coincidence.
It is. And finally, we have Gene students from Brazil. They would like to know how data is downloaded from the Webb Space Telescope and how that is then stored and translated into these images that the general public can access.
Right, well, very interesting question. We talk about data being downlinked, so the spacecraft has a transmitter, an antenna that transmits the signal as radio wave. Not so different as the way your mobile phone transmits your voice and your images to another user. Obviously, the transmitter and the antenna and the receiving antenna and amplifier are much more powerful because we have to cover such a huge distance. But that's how the data are downlinked to Earth. And then they are stored into a database, into computer farms. And that's where the astronomer can download them. So they log into these servers and download the data for analyzing and to understand the science and address their scientific questions. On top of that, I'm sure that NASA will at a certain point make public some images that Webb will provide, the most exciting observations in terms of galaxy or nebulas or even the spectra of some interesting object. There are websites where you can access already beautiful images from Hubble. For example, ESA Sky. It's a ESA site where any user can browse images from space missions, and I'm sure Webb images will land there for the people to download if they want to.
Right, wonderful.
One of the key things to realize also is that some of those data will be released immediately. Some of them might be kept for 6 or 12 months so that the people who propose to do those experiments get the first go at answering the questions. But then all of the data become public. And public to anybody. So you don't have to be an astronomer, you don't have to be at university, you don't have to be in Europe or North America, completely public to the entire world. And what's great about that is that people can go into the old data, if you like. Maybe somebody used it for one question, but you might have a new purpose, another idea about how to use that data. And you can just grab a hold of that and then start doing science yourself. Now that's maybe not the same as just looking at images. You might need to do it in a scientific way, maybe with the help of teachers, whether at school or at university. And we know that happens because in Hubble, there have been projects done by school kids and by university students, and they've gone into the archives from Hubble and found things that nobody else had ever seen. The people who originally took the data didn't discover the things which they found. I think that's a remarkable power of these kinds of missions, is that the data can be used essentially forever after the first purpose. And so, yeah, there are some of you out there who might be thinking, well, how do I get involved? Well, maybe you can make that amazing discovery with Webb that us astronomers didn't even think of in the first place.
Yes, go for it.
Now, I have a final question, and it comes from me. I'd like to know personally, your astronomers, your scientists, what are you most excited about from the Webb data? What are you going to be looking at? Giovanna?
Yes, I'm very interested in the primordial galaxies, so galaxies that are very young. They are, we can see them as they were 13.5 billion years ago. That's the time the light takes to arrive to us. So we see how these galaxies were not long after the Big Bang, which is the beginning of our universe. And with Webb, we will be able to analyze the light, see even further, really the initial stage, understand which elements are there and are involved in the initial process. And that would be very important for us to advance our understanding of how galaxies form.
How about you, Mark?
One of the things I wrote in my proposal in 2002 when I joined the Science Working Group was to point this telescope at the center of the Orion Nebula. This is one of the regions nearest to us which is forming stars today. Young stars and planets are being born there. They're roughly 1 million years old. Now, that for many people that might seem quite old, but compared to our solar system, which is 4.5 billion years old, that's like a 3-day-old baby compared to a middle-aged person. So this is just the very earliest phases of the birth of stars and planets. And what we see in the visible is a region full of gas and dust with some very bright stars in the middle. But when we look in the infrared with a telescope like Webb, we can see through the dust and we can see much smaller young stars and even things which will never actually turn into stars, things we call brown dwarfs. And right at the bottom, the smallest objects we can hope to find are things maybe the size of Jupiter or Saturn, so like planets, but they're not going around stars. They're just going to be floating freely in that nebula. And we don't know how small those objects can be because from the ground we can't see faint enough. With this machine, which can see 100 times deeper at least, so 100 times fainter objects, finally we can answer the question, what are the smallest objects that can be formed in star-forming regions? And I've been waiting decades to answer that question, so I'm really excited now we have the opportunity just in a few months' time.
And I hope you'll come speak to us about that discovery as soon as you figure it out.
I hope so.
Well, thank you so much to the both of you for being our guides today on Webb Quest, for explaining to us the amazing Webb Space Telescope, for diving into infrared astronomy with us, and for also explaining to everyone watching today how they can still be a part of this spectacular mission. Thank you so much to those of you tuning in at home or at school. The quest does not need to end here. Head over to ESA Education's Teach with Astronomy webpage, where you can find more resources, links, and videos about all the topics that we discussed today. And be sure to follow ESA Education on Facebook and Twitter for our next space adventure. Until then, bye from us.
Bye-bye.
Bye-bye.